right, so let's finish off with what we started last time, which is alkene nomenclature, right? We have this new functional group that we introduced, the alkene. That's just a hydrocarbon that now has a double bond in there. And the first thing we discussed, as we're going to do with every functional group that we learn, is how to name them. All right, so take a second, especially for these top ones, see if you can't give you the name of these three compounds right here. So the name of the game here is the same as before, where we want to find that parent chain, that longest continuous set of carbons. So in this case, there are 4. So what's our prefix for 4 carbons? Bute. And since this is an alkene, we're going to have the ending -ene. So this is butene. Remember, the last thing we got to do for our name is indicate the position of that functional group. Since it's between carbons 1 and 2, we would call this 1-butene. Okay. For our next example, we also have 1, 2, 3, 4 carbons in our parent chain. So this is also a butene. But now this is at position 2, because it's between carbons 2 and 3. But this one's also a 2-butene. What's the difference between the two?
Cis and a trans.
Cis and trans, exactly, yep. So this one would be the trans, where they're on opposite sides, and this one would be the cis, where they're on the same side. Notice for this first one, I didn't have to have cis or trans in the name. So why is that? Because if I look here, how many hydrogens are on carbon 1? 2, right? It's got 2 bonds explicitly drawn. So that means there are 2 other groups right there. Since these are the same, since they match, it's not going to have any sort of a cis or trans designation. All right? Basically, you can think about it, if I swapped them, I'd have the same molecule. So there's no stereochemistry for this double bond. And it's whether they're the same no matter what, whether they're hydrogens, whether they're methyl groups, ethyl groups, if they're identical groups, it's not going to have any sort of cis or trans designation in there. It's only in these ones where if I had switched these 2 groups, I would all of a sudden have a different molecule. Okay? So now we got to build on this concept a little bit more, because there's another way that I could name these cis and trans isomers, and that is with this E or Z designation. So E, how I would write that would be E2-butene. So E is like analogous to trans, and Z is analogous to cis. Okay, so these would both be acceptable names for these two compounds. We're going to see why the E and Z designation is actually preferable. It's sort of a little bit more expansive than the cis or trans, and we'll see that in our next examples here. But just note that either one of these would be the same thing. You could say cis-2-butene or Z2-butene. Those are both saying the same thing. Okay, that E and Z are indicating stereochemistry. Sometimes when you have like trouble remembering stuff, the best way to do it is to come up with the stupidest, silliest thing that you can think of, and that'll kind of cement it in your mind. So how I remember this EZ designation is in the Z stereoisomer, they're on Z, ZAME, Zide. Right? Both those groups are on the same side. They're on Z-ZAME, Zide. And if you just remember that one stupid little phrase, you'll always be able to tell E and Z apart. Okay? Great way to remember things. Think of something super stupid that sticks in your head. Okay. So, again, these are equivalent for these two compounds here. You could call this cis-2-butene or Z2-butene, same thing. They're both indicating this molecule here. But E and Z is a little bit more expansive. So what I mean by that is if I go down to this example here, this molecule does not have a cis or trans designation to it. There has to be hydrogens on those two carbons in order to be cis or trans. But this molecule does have E or Z stereochemistry. Okay? So how do we do this? So first of all, name the molecule without worrying about the stereochemistry first. Right? You're going to find the parent chain. We got a butene. It's a 2-butene because of the position of that double bond. And then I'm missing one thing. How do I indicate this substituent here? What do I call this group? The fluoro group, right? So this would be 2-fluoro-2-butene. Let me clean that up. All right, so name the molecule without worrying about stereochemistry first. All right? Now, when we're going to assign the E or Z stereochemistry, step 1, cut at double bond. So what do I mean by that? I'm going to chop this double bond. I'm going to look on either side of the double bond first. Okay? So we're going to do this process for one side of the double bond, and then we're going to do the process for the other side of the double bond. All right, 2. Assign high or low priority for either side. So what the heck do I mean by that? We're going to look at these two groups here. Let me uncolor code this real quick. I'm going to look first on the left side of this double bond, right? So we're going to chop our double bond in half. We're going to look on one side first. So I'm going to focus on this left side. And I'm going to try to assign high and low priority to these two groups, right? So I'm going to compare this group here and this one here. Okay? How do we assign priority? This is based on the atomic number. All right? So I have a carbon as my purple group and my fluorine as this green group. I'm going to assign these as either high or low priority. The higher priority group has the higher atomic number. Okay, so we got our periodic table over here. Let's convince ourselves that fluorine is indeed a higher atomic number than carbon. Actually pull it up here. All right, we're going to look at the atomic numbers of carbon compared to fluorine. Fluorine has the higher atomic number, so it's the higher priority group. All right, so I'm going to go back to my example here. That means that this is my high priority group, and this is my low priority group. So now I'm going to do the same thing on the other side of the double bond. Move this down. Again, my goal is to assign high and low priority for this other side, this right side of my double bond. First of all, you got to remember that there is a hydrogen right here. All right, make sure that we can see where our implicit hydrogens go. So that means I'm comparing, I'll make this bond a little bit bigger. I'm going to compare this group right up here to this group down here. Which one's going to be the low priority group? Carbon or hydrogen? Hydrogen's got the lower atomic number, so hydrogen's going to be the low priority group. And this carbon's going to be my high priority group. All right? So then the last step here is to look at the high priority groups. If they are on Z same side, then it's a Z stereoisomer. If they're on opposite sides, it's the E stereoisomer. So in this case, my two high priority groups are on the same side of that double bond. They're pointed in the same direction. So this would be a Z 2-fluoro-2-butene. All right, unlike our cis or trans designation, this molecule does not have any sort of cis or trans. You can't call it a cis 2-fluoro-2-butene. But it does have E or Z stereochemistry. It is a Z 2-fluoro-2-butene because those two high priority groups are on the same side. All right, so this concept of the E and Z is kind of building off of cis and trans, but you can apply it to other molecules where you can't apply cis or trans to. All right, and the procedure is chop at the double bond, assign high and low priority on one side, assign high and low priority on the other side. Okay, so let's do this molecule here. Again, step one is to just name it like without worrying about stereochemistry. All right, unlike an exam, the stereochemistry would be partial credit for the naming of the molecules. So, right, you could worry about that last. First, make sure you got the nomenclature of an alkene down. Then we can apply our rules for stereochemistry after that. But step one, find that longest continuous set of carbons, find our parent chain. In this case, there's 5 carbons, so I'm going to use what prefix? Pentene. Pent, yep, and it's going to be a pentene because there's a double bond in there. Take a second and see if you can't finish off the name of like the core part of this, and then we'll worry about stereochemistry here. All right, that double bond is located at carbon 2, so it's a 2-pentene. And then what else am I missing? The methyl group, yep, and that methyl group would be located at carbon 3. So 3-methyl 2-pentene. All right, gotta make sure we got that part of our nomenclature down for alkenes. Now we can worry about the stereochemistry. Again, I'm gonna chop, let's do chop at my double bond. I'm going to assign high and low priority on either side. Let's look at the left side first. What's my low priority group on the left side? All right, let's all make sure that we can see that there is a hydrogen here. And so that would be my low priority group, and this carbon is my high priority group. Now when we get to the other side, we got to tie, because this is a carbon, and this is a carbon. Okay, so they have the same atomic number. So how do I break the tie? I'm going to list everything that those two atoms are bound to. So this carbon up here is bound to 2 hydrogens. and another carbon, this one over here. And this one down here is bound to 3 hydrogens. So this becomes my high priority group because carbon, the one that it's bound to, has a higher atomic number, right? It's got 2 hydrogens, these are ties. But now we have a carbon compared to this hydrogen here. So you look at what that particular atom is bound to, and that's how you break the tie. So this becomes my high priority group. This is my low priority group. My high priority groups are now on opposite sides. All right, this one's over here, this one's over here. So what is that, E or Z? E. All right, because they're not on Z same side. Okay? So again, sort of building off this cis and trans concept, we can have E and Z stereochemistry for molecules that don't necessarily have cis or trans. All right, so let's do another set of examples here. All right, what's the parent chain of my first example? Hexene. Okay, I got to indicate the position of that double bond. That double bond, how would I do, what locant we would call it? What number do I give it? 3. And go over here, 1, 2, 3. So this would be 3-hexene, and then we got to indicate that there is a chloro group on carbon 3 as well. All right, now I'm going to go through and do my E and Z stereochemistry. So let me get rid of these real quick. Kind of zoom in here. I'm going to cut the double bond in half. I'll look on either side and assign high and low priority. What's going to be the high priority group on this left side here? The chlorine, right? So I'm comparing the carbon that's located here with the chlorine located down at the bottom. Chlorine has a higher atomic number, so this one's high, this one's low. If I look on the right side of that double bond, which one's my low priority group? Hydrogen. Remember, there is a hydrogen here. Those carbons in those double bonds, they have to be bound to two other things. If it's not explicitly written, that means that there's a hydrogen there. Hydrogen is always going to be the low priority group, right? Nothing's got a lower atomic number than hydrogen. So this one's low and this one's high. So then is this E or Z? Z, right? They're on the same side of the double bond. So Z, 3-chloro, 3-hexene. What's up?
So we only compare the one attached to the double bond and then the next one over, not the ending carbon?
You would only, so the first thing you're going to do is you're just going to look and compare, for example, this carbon and this chlorine on the left side. If they're tied, if they were both carbons, then I would list who they're bound to. But before that, I don't have to pay attention to what they're bound to. I only pay attention to the identity of those two atoms. Right? And then if it's a tie, that's when I have to look at who they're bound to. All right, what's my parent chain for this next example? All right, we all see it's pentene, right? So let's not be fooled by the way that the molecule's written. It's very tempting to say 1, 2, 3, 4. Okay, that's a butene. But remember, you're looking for the longest continuous set of carbons. So I can get even more if I go in this direction here. It's not always going to be written nice and linearly across the page. So in this case, my parent chain is a pentene. I'm going to indicate the position of that double bond. It's at carbon 2. So then I'm also going to need to indicate the position of that methyl group on carbon 3. So kind of the root of this name, 3-methyl-2-pentene. Now I'm going to go and figure out my EZ stereochemistry. Let me actually get rid of these numbers here. Chop at that double bond. Looking on the left side, what's my low priority group? That implicit hydrogen. Means that that carbon's the high priority group. On my right side, this is a situation where now I have a tie, because I'm looking at this carbon and this carbon. Those have the same atomic number. So then I gotta list who they're bound to break the tie. Right? So this is a methyl group, meaning that it's bound to 3 hydrogens. This one's an ethyl group, meaning that it's bound to a carbon and 2 hydrogens. So this carbon, this breaks the tie right here, because this one has the higher atomic number. All right, so they tie on the hydrogens, so I compare a carbon to a hydrogen. So that means that this is the high priority group, and this is the low priority group. So again, I'm not very creative, I guess. This would also be an example of a Z stereoisomer, because those 2 high priority groups are on the same side. Okay, so that's the last bit that we need for our alkene nomenclature. Again, it's kind of analogous to the cis-trans designation, but it's more expansive. Okay, and again, if you have a molecule, so for example, let's just do one more. Like this. This would just be 2-methyl, 2-butene without any sort of cis or trans designation, because these 2 groups right here are identical. Right? If I swapped them, I wouldn't have a different molecule. So it's not all double bonds that will have the stereochemistry. It's if on either side there's different groups. So as soon as I like put an extra carbon here, all of a sudden then it does. But if they're both methyl groups, it does not. Okay. So now we're going to move on to reactions of alkenes. Like we said, our alkenes are more reactive than alkanes because of that double bond. So I made like this little summary wheel of the reactions that we're going to study in this chapter. And I'm going to put it up here, and it's going to look really intimidating and awful. And just trust me, we're going to work our way through it, all right? But I understand what I'm about to show you guys is a little scary. But we'll work through it and break it down and simplify things a little bit here. This is our reaction wheel, what we call a reaction wheel, a summary of the different reactions. So let's just kind of investigate what's going on here. So these are all sort of starting from this middle molecule here. This is my alkene, and there are 6 different reactions that we're going to learn about that transform that alkene into something else, right? What is a chemical reaction? A chemical reaction is just making and breaking bonds. So these reactions here are making these new bonds here. All right, so they're going to all start with the same molecule, the same example, alkene in the middle. And then what's shown here, let's just take one of these for example. This would be one reaction here. So what this is saying is that our alkene, plus in this case bromine, leads to this product here. Okay? We call this, in this case, the alkene would be our substrate. That's what you start with. The stuff that you're using in your reaction we call the reagents. And the thing that you get on the other side is the product. Okay? So our goal by the end of this, really probably the beginning of next week, is given an alkene, we're going to be able to predict what the product is given a reagent. Okay, that's our goal here. I'm not going to make you guys memorize the reagents, but you do need to be able to sight recognize them, right? So I'm not going to be asking you to explicitly draw in the reagents, but if I put down a substrate and a reagent, you have to be able to tell me what the product is. Okay? Now again, I know this is really intimidating to look at, but let's sort of break it down real quick. All of these reactions share one very important common thing, and that is you are breaking the double bond and adding something to either side, adding something to either carbon. Right? They all share that one feature. You start out with this alkene that has a double bond, and in your product you now have 2 new things that are bound to what were formerly those 2 carbons that were double bonded together. Okay? These are what we call addition reactions. All right, a big part of organic chemistry is taking a functional group and kind of like categorizing the type of reactions in it. Alkenes undergo these addition reactions where you're adding something to either side of that double bond. Okay? So they all share this common feature. You're breaking that double bond, and those 2 carbons are getting something new bound to them. All right, so we can all see that, right? These addition reactions. Okay. They also notice that in each case, it's either going to be a hydrogen that's being added, an OH group that's being added, or a halogen that's being added. They're kind of different combinations in thereof, but it's always one of those 3 things. A hydrogen, an oxygen, an OH group, or a halogen. Right, in all 6 of these different reactions. All right, so these are kind of these common features that they share. Now we're going to look at each one individually here. All right, so we're going to start with this one here. Okay, so if I have an alkene, I treat it with HBr or hydrobromic acid. Doesn't really matter if you know the name. Treat it with HBr. What's going to be added to either side of that double bond, right? So right off the bat, because they all share this same feature, I know this carbon and this carbon are going to have two new bonds. So I can start these problems the same way for every single reaction that we learn. I'm going to take those two carbons, I'm going to take away that double bond between them, and I'm going to add a bond to either side. We can do this for every single reaction that we're going to learn for alkenes. This same strategy will work, right? It's just a matter of who's being added to those two carbon atoms there. And in this case, not surprisingly, it is a hydrogen and a bromine.
How do you figure out which one goes where?
That's a good question. I'll get to that in 1 second. All right, but just for now, let's convince ourselves that we can see this addition reaction here. It's a very good point. Which carbon do I put the bromine on? We'll talk about that here in a second. But for right now, let's just make a note of this addition reaction. Again, I can just start by taking my molecule and drawing two new bonds on the carbons that used to be double bonded together. I'm going to be adding something to them. In this case, it's a hydrogen and a bromine because my reagent is HBr. Okay? To address the question of where the bromine goes. So first of all, I'll just tell you the punchline here. Br goes on the more highly substituted carbon. What do I mean by highly substituted? This is that primary, secondary, tertiary business that we talked about. Primary more than secondary beats, tertiary's better than secondary, better than primary, right? So the bromine goes on the carbon that has more carbon-carbon neighbors. Okay, so that's why I picked carbon 2. Right, so this is carbon 1, this is carbon 2. That's why I put the bromine on carbon 2 instead of carbon 1. Because carbon 2 has two carbon neighbors, carbon 1 only has one carbon neighbor. Right, carbon 1 is a primary carbon, carbon 2 is a secondary carbon. Okay, so it's going to go on the more highly substituted carbon. So why that is we need to look at the intermediate for this reaction. So this is where our electron pushing arrows are going to come into play here. We're going to look at this reaction mechanism. The first step in this reaction is this pair of electrons that used to be in that double bond are going to reach out and grab that hydrogen, and that breaks that HBr bond. All right, I'm going to be good and put in lone pairs here. So my product from this step of the reaction, first of all, is that bromide ion. All right. Notice that it has an extra pair of electrons because what used to be this pair here in this bond, when that bond broke, that pair of electrons went up onto that bromine, making it the bromide ion. All right. Now there's a hydrogen bound to this carbon here. So this pair of electrons that used to be my double bond is now in this pair of electrons here. Okay? And I'm missing something really important from my intermediates that I've drawn here. So this is what we call this. These are our intermediates of this reaction. Again, we know the product is going to look like this. This is our intermediates that we get here. Does anybody see what I'm missing from my intermediates? There's this really important concept of conservation of charges, right? At every step, you should have the same number of atoms, the same number of electrons, all that good stuff. I started out with 2 neutral molecules, so what am I missing?
The positive charge.
I need a positive charge in there, right? Because I created this negatively charged bromide ion. At the same time, there has to be a positively charged something that's created. All right, and that positive charge is going to go on this carbon here. So why is that? I want everybody to kind of convince themselves real quick that this carbon, let's color it, this purple carbon here, got that green pair of electrons taken away from it, right? When that double bond became this new hydrogen carbon bond, that pair of electrons, that green pair of electrons was snatched away from that purple carbon, leaving it with less electrons and a positive charge. Okay, and again, an easy way to spot this, make sure you're paying attention to charges, is if you create something negative, you started out with something neutral, you create something negative, something positive's got to be in there as well. Okay? So this is explained, so this mechanism here, if we finish it off, this bromide, this bromide ion will attack, that was terrible, will attack that positively charged carbon. Okay, that finishes off my reaction mechanism. But this explains why the bromine will go on the more highly substituted carbon. Why is that? Well, similar to how we talked about the stability of radicals being different depending on the level of substitution of the carbon, we have the same thing with these positive charges, what we call carbocations. Remember, cations are positive, so a carbocation is a carbon that has a positive charge. Tertiary carbocations are more stable than secondary carbocations, are more stable than primary carbocations. All right, so the intermediates for these reactions, these carbocations, explain why there's a specificity as to where that bromine goes. All right, and again, it's the exact same trend that we saw for our free radicals, but this is increase in stability, increasing stability. All right, again, this primary, secondary, tertiary designation was something that we talked about in chapter 1. Let's make sure that we can see what's going on here, because this is an important part that we don't want to miss here. Again, we call this a secondary, in this case carbocation, because that central carbon is bound to 2 other carbons. Right? A primary carbocation, that central carbon is just bound to 1 other carbon. Tertiary, it's bound to 1, 2, 3. So again, that's kind of why we bother with this primary, secondary, tertiary designation, is so we can talk about stuff like this. Stability of carbocations, stability of free radicals, etc. Okay? But again, long story short, the bromine is going to go on the more highly substituted carbon. Okay, so let's see an example of what I might ask you for this. I'm going to give you a substrate. Give you these reagents. And I can ask you 2 things. 1, draw the product. And 2, draw the carbocation intermediate. Those are the 2 things we want to be able to do for this reaction. All right, so again, I'm going to color code my 2 carbons here so we can keep track of who's who. All right, the first thing I can do, and I can do this for every single one of these reactions that we're going to learn in this chapter, is to just take those 2 carbons and draw 2 new bonds, because something's going to be added, to one of those 2, or to both of those carbons. That's going to be the same for all of these addition reactions that we're going to see. So first step I can do is just take that same molecule that I started with, break that double bond, put 2 new bonds on either side. We're going to have to fill in what they are, but that strategy will work for every single reaction that we learn here. All right. Now I'm going to have to add an H and a Br. Which carbon is going to get the bromine, the red or the green one?
Red.
The red one, right? The more highly substituted one. In this case, be this red one, because that red one is a tertiary carbon compared to the primary carbon in green. All right, so that's how I'm going to figure out which carbon to add the bromine to. Then I'm going to have to draw my carbocation intermediate here. All right, and is that going to put the positive charge on the red or the green carbon? Red, right? That was the whole logic as to why the bromine got added there, is because the tertiary carbocation is the more stable. So that would be the intermediate of that reaction, where the positive charge goes on the more highly substituted carbon. Okay. This whole, the bromine goes on the more highly substituted carbon business has a special name that you've probably come across, and that is some Russian dude's name, Markovnikov. This would be considered a Markovnikov reaction because the bromine goes on the more highly substituted carbon. All right. Markovnikov was clearly this Russian scientist who first studied these types of reactions. Okay, so check. That gets us this one here. All right, so that's that first reaction. Now we're going to take a look at this one here. Okay, so my reagent is again, or my substrate is again just an alkene, but now instead of treating it with HBr, I'm going to treat it with Br2. Okay, let's start with our same molecule here. Again, I'm going to treat it with, in this case, just bromine, Br2. And again, my strategy for drawing my products, I can do the same thing for every single reaction that we learn. I'll color code these. So I'm going to start with my original molecule and then draw two new bonds. One on what was formerly that green carbon and one on that red carbon. All right. And now what I'm going to be adding to either side of those double bonds is just going to be a bromine. Br2. I got two of them in there, right? So one's going to go on one side, one's going to go on the other side. They're the same thing, so good news, we don't have to worry about any Markovnikov business. All right? There is other consideration. So we do also want to be able to draw the intermediates for these reactions. Okay? So how that's going to look, show you our reaction mechanism, our electron pushing arrows here. It's kind of a weird one. It starts out the same, where this pair of electrons is going to attack, in this case, the bromine. But then the bromine attacks kind of right back. This bond breaks. And this forms a cyclic intermediate here. Okay, where now my carbon, I know this is a weird looking one, so just bear with me. All right, this forms what's called a cyclic intermediate. You've created this three-membered ring with two carbons and a bromine. It forms a little triangle looking thing. It's got a cool name. This is what we call a bromonium ion. All right, those are the intermediates for those reactions. This cyclic bromonium ion. All right, and then if I finish out my mechanism here. Whoops, that's actually not finishing it out. That goes there, that breaks there. Don't worry about drawing the mechanism. I mean, the mechanism explains where the electrons are going. For this particular one, it's a little bit crazy, so let's not focus too much on that, but let's make sure that we can draw the cyclic bromonium intermediate here. Okay? So if I give you a new one, we'll use that same example we did before. Again, you're going to want to draw me the products and that intermediate. My products are pretty straightforward because, I'm just adding the same thing to either carbon, so nothing too crazy there. Same strategy, I'm going to draw my same molecule, but without that double bond, two new bonds on either side, on either carbon. The weird one here being that cyclic bromonium ion intermediate. So what I'm going to do is I'm going to again take that kind of like shell of my molecule, but now to either side of that double bond, it's created this cyclic structure here with the bromine. All right, so it's a triangle with the bromine sitting at the top of the triangle. All right, an important thing that we need to make sure to draw as well is that this bromine, because it has two bonds, has a positive charge. All right, so for these reactions, we want to be able to draw our product as well as the intermediate, that cyclic bromonium ion. All right, we'll work our way through the rest of that reaction wheel next class.